In this video, I'm going to be going over the solution to question 1 on quiz 6. So notice that question 1 here was asking you to evaluate the integral of 5x minus 12 over x times x squared plus 4. This is a rational function. So when we think about our different integration techniques, with many rational functions, we're going to want to use partial fractions unless u substitution would be easier. But notice that my denominator here would be x cubed plus 4x. So du of that would be 3x squared plus 4, and I just have an x in the numerator. So u substitution isn't going to work. I do need to use partial fractions. Okay, so we need to remember what the partial fraction decomposition form is, figure out the form, find our unknown coefficients, and then go about integrating the sum of those simpler pieces. So I noticed a lot of people wanted to just write that this integral was equal to that partial fraction form, but that would not be correct. What we want to do is take this integrand out here separately and say, okay, 5x minus 12 over x times x squared plus 4, okay, which has this simple linear factor here, and then this x squared plus 4, which is an irreducible quadratic because we can't factor that anymore, okay, will be equal to some a over x plus some bx plus c over x squared plus 4. Okay, notice I'm not going to say that this integral is equal to the sum of a over x plus bx plus c over x squared plus 4, because this integral is going to be equal to something else. We're going to have to do the antiderivative. It's just the integrand itself that can be replaced by the sum of these two fractions. So I noticed a few people put just b over x squared plus 4 instead of bx plus c. So I just want to show you what happens if you thought that and why that would not work out for you. So if you thought that the form here was a over x plus b over x squared plus 4, that would mean after you cleared the fractions, after you multiplied both sides by x times x squared plus 4, that 5x minus 12 was equal to a times x squared plus 4 plus bx, meaning that you would have ax squared plus 4a plus bx equals 5x minus 12. Okay, so then equating the coefficients, that would mean that this a over here was equal to 0, because there's 0 x squareds on the left, that this coefficient of x here of b would be equal to 5, the coefficient of x over here, and that 4a was equal to negative 12, the constant term. Okay, well that tells us then that we both have a equals 0 and a equals negative 3, so that's just not possible. Okay, so it can't be that 5x minus 12 over x times x squared plus 4 is equal to just a over x plus b over x squared plus 4. So we really do need that bx plus c part here to get a correct breakdown of our rational function here into these two simpler pieces. Okay, so I just wanted to remind you, why that form is necessary. Okay, so we do need to go about finding our a, b, and c. So I'm going to clear the fractions, which means multiply both sides by x times x squared plus 4. Okay, so this is why that left-hand side simplifies to 5x minus 12. And then I'm taking a over x times x squared plus 4, so the x's cancel. So we have a times x squared plus 4. And then we're taking our second fraction here times our x times x squared plus 4. The x squared plus 4's cancel. So we have bx plus c times x. Okay, so I noticed that some people are writing down just this part without the equals 5x minus 12. You do need both sides because you have an equation that you're working with, and then you're trying to find what values of a, b, and c make that equation true. So you need both sides here. Okay, now we do have a couple of options with how we can solve for our a, b, and c. You can plug in 3 different values of x to get your set of equations. You can also expand out this right-hand side and then equate the coefficients. In this example, it's just a little shorter to equate the coefficients, but it's perfectly fine to also, or to choose to do the method of just plugging in 3 different values for x. So I'm going to show the method where I get, where I'm going to equate the coefficients. So I'm going to have to expand over here. This is ax squared plus 4a plus bx squared plus cx. Okay. So I notice that I have this ax squared and this bx squared. So that means I have a plus b x squared terms on the right, and I have 0 x squared terms on the left. So I get the first equation for my system of equations here being that 0 is equal to a plus b. For the x coefficients, I have 5 x's on the left-hand side, and I have just c x's on the right-hand side, so I get exactly that 5 is equal to c. And then for the constant term, notice on the left-hand side that constant term is negative 12. I think some people might have said it was 12, but you do have minus 12 there, so that's actually a negative 12. That's equal to our constant term over here on the right-hand side, which is our 4a. Okay, so that gives us that a is negative 3, and then if a plus b has to be 0, that means b has to be positive 3. Okay, so we see how this set up a pretty simple system for us. Okay, so now we're ready to use our partial fraction form to actually evaluate the integral. So we can say that our integral of 5x minus 12 over x times x squared plus 4 dx is equal to the integral of our a over x plus our bx plus c, where c is equal to 5 over x squared plus 4. Okay. So the one that is, or the part of this that's a little bit trickier is the second integral. So we know that the integral of our negative 3 over x is going to be negative 3 log absolute value of x. Okay, and then we're going to need to integrate this 3x plus 5 all over x squared plus 4. So there's several different ways that you can do this. One way, okay, so method 1 would be to use some trig sub. So you could let x be equal to 2 tangent theta, so that dx would be equal to 2 secant squared theta d theta. And then you could say that your integral of 3x plus 5 over x squared plus 4 dx is equal to an integral of 3 times x, which would be 2 tan theta, plus 5. And then all of that in parentheses would be times the dx, so that would all be times 2 secant squared theta d theta, and this would be all over x squared plus 4, which would be 4 tan squared theta plus 4. Okay, so one way to do this would be to use our trig sub. We'd have to use the identity on this, get some cancellation, but then this would still break up into 2 integrals because I do have a plus 5 here. So why don't I go a few steps further just to show this method. So there are a few people who tried to do the trig sub method, but sometimes it got a little bit mixed up. So notice that this 4 tan squared theta plus 4 would be 4 secant squared theta when we use the identity. So the secant squareds here would cancel, and I would also be able to simplify that 2 over 4 and just have 2 as the denominator. So notice that I would have this 1/2, the integral of 6 tan theta plus 5 d theta. Okay, so this would give me, let's see, if we multiplied this through, I would have 3 times the integral of tan theta d theta plus 5/2, an integral of just d theta. Okay. So I'm going to stop there, but you could keep going with that method. Now, that gets a little bit messy with trig sub, but it's a perfectly valid method. What else could we do besides using some trig sub? Well, I could split the integral up right here and have 3 times the integral of x over x squared plus 1 dx, or excuse me, x squared plus 4 dx, plus 5 times the integral of 1 over x squared plus 4 dx. and integrate each of these two pieces. So why is this easier? Well, the first integral here, this x over x squared plus 4, I can use u substitution on. I can't use u substitution on this whole thing to begin with because of me having this 3x plus 5 here in the numerator. But let's see what u substitution looks like on the x over x squared plus 4. So I could use u is equal to x squared plus 4. So my du is 2x dx, or 1/2 du equals x dx. So this gives me negative 3 log absolute value of x plus 3. This is going to be 1/2 du over u. Okay. And then I have plus 5 over 1 over x squared plus 4 dx. Notice that the reason I can't use u substitution on this second integral is similar to why I can't use it on the combined integral. If I let u be this denominator, that's fine, but then I don't have any way to deal with my dx here, because my dx in terms of u would have to be like 1 over 2x, so I don't have an x in the numerator here to replace with my du. Okay, so u substitution doesn't work on this second part, at least not this particular u substitution. Okay, so we have a couple of options that we can do on this second integral. You could do the trig sum just on this second integral using x equals 2 tan theta and dx equals 2 secant squared theta d theta. That will end up giving you this 5/2 integral of d theta, okay, because you'll end up with the dx will be 2 secant squared theta d theta. The x squared plus 4 part will become 4 secant squared theta. So you'll have 2 secant squared theta over 4 secant squared theta, which will end up being just 1/2. Okay, so this will be 5 the integral of 1/2 d theta, or 5/2 the integral of d theta, like we see here. Okay, so notice that that part would become 5/2 theta, and because x is equal to 2 tan theta, okay, that means we know x over 2 is equal to tan theta. So theta itself would be equal to tan inverse of x over 2, or arctan of x over 2. Okay, so that's one way to see what this integral would be, was to use a trig substitution. Okay, so we have two other options for dealing with that integral. One is to do a u substitution, and two is to use a rule. Okay, so there is a rule in the textbook that the integral of 1 over x squared plus a squared dx is equal to 1 over a arctan of x over a. Oops, I wrote x over 2. In this case, our a is 2, but in general, it would be x over a plus c. Okay, so that's how we could get 1/2 arctan x over 2, and then that's being multiplied times 5 to get the 5/2 arctan x over 2. Okay, so we've got a trig sum method we can do. If you can remember this rule, you are allowed to use this particular rule on things of the form 1 over x squared plus a squared. And the other option is to do a u substitution. In the original lecture where I was explaining this, I used u substitution. I find that easier because I sometimes forget exactly how the constant in front of here is going to be, that it's going to be 1 over a and not just a. So just to make sure that I get the right antiderivative, I prefer to work out the details. But if you can remember this rule, you are allowed to just use this rule. So let me just show that other substitution that we can do. Notice that that x squared plus 4 I can write as 4 times x over 2 squared plus 1. Okay, notice that if I multiplied the 4 back through, we would get x squared plus 4. But this allows me to do a substitution with w equals x over 2. And so my dw is 1/2 dx, or 2 dw equals dx. Okay, so let's go down here. We have this equals negative 3 log absolute value of x plus 3/2. This integral of 1 over u is going to be log absolute value of u. I've got this 5/4 from pulling out this 4 here, and now I've got this integral of 1 over w squared plus 1, where dx is equal to 2 dw. Okay, and so now instead of having to remember this special case of the rule for the integral of 1 over x squared plus a squared, I can just use my standard rule that 1 over x squared plus 1 is equal to arctangent of x. Okay, so we have negative 3 log absolute value of x plus 3 halves log of our u, where u is x squared plus 4. Okay, this will be 5 halves when I simplify this 5 times 2 over 4, and I'll have this arctan of w okay, oops, plus c. Okay, and then notice that our w was x over 2, so I can get to the final answer here of negative 3 log x plus 3 halves log of x squared plus 4 plus 5 halves arctan of x over 2 plus c. Okay, so I've written a lot of different things on here just to show you do have multiple ways of handling integrals of this type, of this like 3x plus 5 over x squared plus 4, something linear over something quadratic. That's a form that comes up all the time in these partial fractions, so you want to make sure you're comfortable with one of these different methods for handling integrating something of that type. Okay, notice with the trig sum over here I didn't quite finish, but this will be 3 log of the absolute value of secant theta for tangent. Okay, and this will be using the triangle here. All right, we can go ahead and finish it up. Notice that we have x over 2 is tan theta, so this is x over 2 if this is theta. So this is the square root of x squared plus 4. So secant theta would be our hypotenuse over adjacent, so the square root over 2. So I know I'm running out of room here to show this alternate form here. So this is 3 log of the square root of x squared plus 4 all over 2. And then we had the 5 halves arctan x over 2. Okay, so how does this compare to what we found over here? Well, we see the 5 halves arctan x over 2 is the same. This 3 log of the square root of x squared plus 4 over 2, we can show we're going to get something like this by using some log rules. Notice that log of a quotient will be log of the numerator minus log of the denominator. So you're going to get an extra, what looks like an extra constant over here in this form, but we think of that just being absorbed into the plus c. The 3 halves part would come about because I'd have this x squared plus 4 raised to the 1/2 power, and when I have log of something raised to the power, you can bring that power out in front times the constant. Okay, so this is the same over here. That's what I just want to point out. But any of these methods would be fine. You just need to make sure you're comfortable with one of them. Okay, so let me know if you have any questions on that example.